So I'm going to talk about KPZ fluctuation, but in a slightly unusual setting, that is in a finite volume. So you're not on an infinite line, but you have particular boundaries. So first, I will recall you a few things about the setting. And then I would be interested in what happens in the late time limit, in the long time limit. In particular, there are two ways to get the current fluctuation, the fluctuation of the height or the current in the long time limits. So first, there is an iterated version of the matrix product ansatz, which gives you some expression in terms of non-intersecting Brownian paths. And then there's Bethe ansatz for, I mean, this, the first approach works for any initial condition. But then from Bethe ansatz, you can get some rather explicit expressions for simple initial sets. And so if I have time in the end, I will talk about the dynamics, not just in the long time limit, but at finite times, where it involves a Riemann surface. So about KPZ fluctuations in one dimension, so probably all of you know about what I'm going to tell you. So, I mean, we have a universal function, a random function, 8h, which depends on the position x and time tau. And for instance, this can be, I mean, one way to define it is the KPZ equation. And so the KPZ equation, so in principle, you have several parameters, one in front of the smoothing term, one in front of the growth term, and one in front of the noise. But you can absorb these parameters. So if you're on the setting of the infinite line, you can absorb, in fact, all the parameters. But if you are in a setting where your system size is finite, you want to keep your size finite. Let's say I will be in this talk taking x between 0 and 1. Then you can't absorb all the parameters. So you have this parameter, for instance, lambda, that stays here. And you have a different dynamics that, depending on lambda. And so lambda going to 0 will be the equilibrium fixed point. You don't have the KPZ growth term. And here I will be interested in the other limit, lambda going to infinity, which is the KPZ fixed point. So, I mean, in the setting of the infinite line, you don't have to care about this because, I mean, as time progresses, it corresponds to having lambda going to infinity. So the dynamics gives you the crossover between the equilibrium and the KPZ fixed point. But in a finite volume, you really have a dynamics which depends on lambda. So, I mean, this is one of the settings, interface growth, where you see KPZ, and of course, there are many other settings, fields or random geometry. And so, as your correlation length grows as time to the power 2/3, if your system size is finite, at some time your correlation length reaches the full system size, and that's when the boundary conditions become important. So in order to study this KPZ dynamics at the KPZ fixed point, it's useful to look at discrete models. In particular, the one I'm going to look is TAZEP, so which is integrable and from which you can compute things quite easily. So I will be looking at a setting where you have TAZEP on a finite interval. So I will have L sites, and I will have boundaries. So I will talk to you about it later. Mostly about it will be open boundaries. And so KPZ, I mean, the KPZ fluctuation are seen in the statistics of the current. So the current, what I call QIT, is a time integrated currents between site I and site I plus 1, so total number of particles that have crossed from site I to site I plus 1 between time 0 and time t. So, I mean, there's the usual mapping to interface growth, and so the current is essentially the same as the 8. And of course, we want to look at this model at large L. And so there are two interesting timescales. The Euler timescale, so times of order L, where at leading order, the evolution of the density profile is deterministic. So it follows Burger's equation, and so you have some dynamics with shocks appearing and mergings. But for times now much larger than L, this density profile converges to a completely flat density profile. And now on the KPZ timescale, you only see fluctuations of order square root of L around this flat profile, or 1 over square root of L, if you, I mean, depending on how you normalize. And so the KPZ field emerges like this universal KPZ field, h of x of n tau, is this constant here. So as usual, you have to subtract the velocity of the 8, and also depending on the kind of initial condition you choose, you have some constant here you need to subtract, which is the contribution of the whole Euler scale to the 8. So as I said, since the correlation length will span the whole system, well, boundary conditions will be important. I mean, you will have different fluctuations, different objects depending on the boundaries. So, for instance, you can consider periodic boundaries, so x equal x plus 1. And so for TASEP, it means that your number of particles is conserved. So in particular, you have a density of particles, which is number of particles divided by the system size. But it turns out it gives you, I mean, independently of your density of particles, you get exactly the same field h of xt. The density of particles just comes as a prefactor in the time and the position and so on. While for open boundaries, so you consider this model. So this, I mean, this is the model I will be mainly interested here. So you have two rates, alpha and beta, so the rates at which particles enter the system and leave the system. And so, as you probably know, so you have some non-trivial phase diagram for this model. So you have 3 phases. 2 phases, low and high density, where essentially your system is either completely full or completely empty, and your I mean, the fluctuations of your systems just happen at the boundary. And so you have a non-trivial phase, which is called usually the maximal current phase, where your system, I mean, on average, half of the sites are occupied, half of the sites are empty. And so you see the KPZ fluctuation only in this phase and at its boundary. More precisely, so, I mean, having these rates alpha and beta means you fix the density of particles on the left and on the right. So in terms of the KPZ8, you fix the slope of the KPZ8 on the left and on the right. Of course, I mean, this is not really so precise because h is not some differentiable function, it's very rough, but if you want on average, it's true on average at least, that the special derivative of the average 8 at position 0 will be some value and will be another value on the right boundary. And so you find this boundary slope sigma and sigma b when you're close to the, in the vicinity of the triple point, so at a distance of 1 over square root of L. And so the maximal current phase actually corresponds to having infinite boundary slopes. So sigma A equal to minus infinity, sigma B equal to plus infinity. So this is a completely different setting from the one with periodic boundaries. But there are some things a bit strange for alpha equal 1, beta equal 1/2, and the opposites. It turns out that some quantities are exactly the same as for periodic boundaries, not all quantities. The quantities I'm talking about are large deviation function of the current. But for instance, if you look at the stationary measure, the stationary measure is really not the same between these two cases. So it's a bit, we don't really have a good explanation why there is this coincidence here. And also another type of boundary you can consider is when you have a system with periodic boundaries, but you add a system with a second class particles. So a particle, the white particle here, which moves, it moves on empty site like a normal particle, except with some rate alpha. But the normal particles have priority with respect to the second class particle. And so this can be seen as a kind of boundary condition with a moving boundary. And again, there seems to be, at least at the level of stationary large deviation, some relation between this kind of open boundary, this kind of moving boundary and usual open boundaries, at least for alpha equal beta equal 1.
Is that more integrable for general alpha and beta, the last one?
Sorry?
Is it integrable for general alpha and beta?
Yes. It's even integrable when you have an arbitrary number of second class particles. You have papers by Luigi Cantini. I will talk about it later. And so here I'm interested in the fluctuations of the current. So remember, QIT is the total number of time particles have crossed from site I to site I+1 up to time t. And so, this TASEP is a Markov process. So you have your Markov generator M, and there is a deformation of this Markov operator when you multiply all the transition, all the matrix elements in M by corresponding to a transition where a particle moves from I to I+1, you multiply them by G. So you have this, this new matrix, this deformed matrix, and it turns out you can show quite easily that this average here is equal to, is given by, in terms of this propagator, exponential times mi of G. And so, it depends on I, but in a sense that, you have some similarity transformation that can change the value of I, similarity transformation, which is diagonal in the configuration space. So, it's quite easy to go from any value of I to any other value of I. So this is for the model with a finite number of sites, finite number of particles. But then you want to look at what happens at large scales. And so it turns out that if you look at the spectrum of this matrix, so for a finite system, here it's with periodic boundaries, it looks like this. So you see you have these peaks, and if you look at the central peak here, it turns out that the eigenvalues here are of order 1 over L to the power 3/2. And these are the eigenvalues that contribute on the KPZ time scale, time of order L to the power 3/2. And you have only the eigenvalues that are close to here, which contribute to the KPZ time scale. So this picture, it's actually a bit reminiscent of what is called the Luttinger liquid. So because the spectrum here is the real part and the imaginary part of the spectrum, but it turns out the imaginary part is proportional. I mean, for the eigenvalues close to the right, the imaginary part of the eigenvalue is proportional to the momentum of the excitation corresponding to the eigenstate. And so you have this kind of peak structure, which is essentially the same as in a Luttinger liquid, except that you have a different scaling. For Luttinger liquid, you have always a scaling 1 over L here, and for all the peaks. For KPZ, so all the peaks contribute on the time scale where you get conformal invariance. But on the KPZ time scale is different. Here you have 1 over L to the power 3/2, while the other one, the scaling is 1 over L to the power 2/3. So they won't contribute in the KPZ time scale. So anyway, what you get in the end is something like that for this generating function for the 8 fluctuations. We have an infinite sum over all the excitations. But here I will be interested only in the late time behavior. So you will have only the contribution of the eigenvalue with largest real part. And so you have two terms. So, I mean, you have two terms in the exponential. So this mu st is the eigenvalue. And you have some correction here, which comes from the contribution of the eigenvector, of the stationary eigenvector on the left, on the right. And you see that in the long time limit, since you have a sum of exponential, this equality is true up to exponentially small correction in time if the time is long enough. So essentially, for a time long enough, you only see this part. And in particular, so the green part here, the stationary large deviation, is something which is independent of the initial condition, while all the dependency on the initial condition that is left is contained in this new st function. And in particular, it's also true for the cumulants of the 8. If you take derivative at successive derivative at s equal to 0, you have the stationary cumulant plus some correction plus which is independent, which depends on the initial condition, plus exponentially small correction. Okay, so the thing you would like to compute is so this correction here. I mean, this is what I'm interested in here. And so there have been two main approaches to compute this. So one approach, which is based on the matrix product ansatz for the stationary state, some extension of it, and the other one, Bethe ansatz. So the first approach is perturbative in this parameter S, the parameter which comes here. In some sense, you just need to iterate your matrix product representation to get, any order in S. And in this approach, it's quite easy to take the large L limit, actually, and you can show that this gives you two extreme value statistics of some Brownian paths. So the kind of Brownian path you get depends on the kind of boundary condition you have. And then you have Bethe ansatz, which in principle give you all the eigenvectors. I mean, which does give you all the eigenvectors. And in principle works for any initial condition, but you get rather explicit expression only for a simple initial condition. These two approaches are a bit orthogonal, and then you can put them together to see, to compare the results that you get from them. And it gives you some nice conjectures for these these Brownian paths. So for example, this one, it's the thing you get from open TASEP with alpha equal beta equal 1/2, which is in some sense the simplest case. So the first approach gives you something which involves independent linear processes. And the other side gives you some rather explicit function. And the claim is that these two things are equal. So on the left, it's something which is, it comes from a perturbative expansion. So you expand up to some arbitrary order. And here it's some function of the variable s. So this is a special case, but in general, you get something, the kind of process you get here and the kind of function you get here depends on your boundary conditions. But it will always give you some kind of Brownian process. It can be a Brownian bridge or involve Brownian excursion and so on. And on the other side, give you some function which has actually branch cuts in the complex plane. The extension of this function to its Riemann surface will be involved in the full-time dynamics. Okay, so now let me tell you more about these two approaches. So first, let me begin with this iterated matrix product approach. So, first, let me remind you about the stationary measure of TASEP. So, this stationary measure is just the Perron-Frobenius eigenvector of your Markov generator. So in principle, you can give the stationary probability for any configuration. But here it's usual not to think in terms of configuration with position of particle, but more in terms of the height function. So the height function, which is, so if you call ni the occupation number of the particle, so ni equal to 0 is an empty site, ni equal to 1 is an occupied site. So the height function is given by this. So it's depicted here. So it's a discrete height function, and in the KPZ scaling limit, it will give you some stationary random field, which is a random continuous function. Now you have some simple cases where this is quite simple. So either open TASEP with alpha equal beta equal 1/2, or periodic TASEP. In both cases, the stationary measure is uniform. And so, for instance, in the open case, you get a discrete height, which is just some random walk where you have a probability 1/2 to go up, 1/2 to go down. So this, in the scaling limit, just gives you a Wiener process. For periodic TASEP, it's almost the same, except you get what is called a Brownian bridge. So it's a Wiener process, which is conditioned to come back at the same value at x equal to 1. So these are the two simple cases, but in general, you get a matrix product representation for the stationary state, from which you can get these height field, the stationary height field for general boundary rates. So, it's quite easy actually to get it from some rewriting of the matrix product representation, some rewriting that is used then in this iterated procedure that I'm going to talk about next. So let me remind you, so the matrix product representation by these people. So you want the stationary probability of some configuration given by occupation numbers, n1 up to nl. And so it's given by this, this kind of expression where you have two matrices that enter depending on the occupation that are traditionally called D and E, and you have some simple algebra. But there's actually another representation for this, which makes things much simpler in the end to take the scaling limit. It's a kind of representation in terms of a marginal process. So here you have the probability of just one configuration. You rewrite this as a marginal of some probability of two configurations, which has a matrix product like this. So now it depends on the occupation numbers of the two configurations with these matrices. And so why does it work? Well, now you want to show that this gives you this. So you sum over C prime. So if you sum over C prime, you always have x 0 and 1 plus x 1 and 1. And x 0, 0 plus x 1, 0 is d minus identity plus identity, so it's d, and same for the other one. So it obviously works that this gives this. But why is it useful? It's because the algebra, in terms of this small d and small e, is much simpler. I mean, you can see that this becomes just dE equal identity. And now there is actually simple way to represent this Q of C and C prime in terms of the H function. So in order to see that, so you have the H function associated, HI associated with C, HI prime associated with C prime. And so let's draw here, let's plot HI, the difference, HI minus HI prime. So you see that it goes up, so it's constant if the occupation number Ni equal Ni prime, and it goes up or down if they're different. And from this, this matrix is here, you see that if this A different goes up, it's associated with the matrix E. If it's constant, it's associated with the identity. And if it goes down, it's associated with small b. Q of C and C prime is equal to this. Now this, you can reduce it using, you can remove the identities and you can use the algebra dE equal identity. And dE equal the identity, it means you can erase any of the local minima. But when you're doing this, you see that the maximum of this curve does not change. And so what you end up with after erasing after using repeatedly this, is e to some power, which is equal to the maximum of this curve, hi minus hi prime, times d to some power. And you see that the total number of e's minus the total number of d's is also preserved. So now if you use in the end the boundary algebra, you see that Q of C and C prime has this simple expression. So you have the maximum of H minus H prime. And also, N and N prime are the total number of particles in the configuration C and C prime. So you see that you get something very simple. And actually, this thing in the scaling limit is also simple. So you get two random walks, H and H prime. And in the scaling limit, these two random walks just give you linear processes when you rescale it properly. And so you get that your KPZ 8 is a marginal of some process where you have two random 8, which are independent linear processes reweighted by this density here. And so, for instance, let's look at the case where the boundary slopes are infinite. So sigma A equal minus infinity, sigma B equal infinity. So because of this, you see that you need to have the maximum of H1 minus H2 is equal to 0. You also need H1 of 1 minus H2 of 1 is equal to 0. So it means that your two paths, H1 and H2, are random paths like this. So they start at 0, they don't intersect, and they end up at the same point. And actually, there's another representation for this, completely equivalent. in terms of the Wiener process and a Brownian excursion. A Brownian excursion is a Wiener process which is conditioned to stay positive and come back to the origin. And you can show that this representation here, this representation here with these non-intersecting processes that go back to the same point is the same as the top one being a Wiener process plus an independent Brownian excursion divided by square root of 2. And the bottom one is the same, but with minus the Brownian excursion. And so we recover here the known representation for this stationary 8 as was found by these people. So in this special case with infinite slopes. So this was for the stationary initial condition. It was for the stationary state. But now let me remind you, I want to compute this in the long time limit. So in the long time limit, I have only the contribution of the stationary eigenvector, the eigenvector depending on G, which has the largest eigenvalue. And it turned out that there is a representation for this, which is a kind of iterated matrix product representation, which was found by Alexandra Darescu with a former PhD student of Kiron Malik. There is some transfer operator U of G, which has a matrix product representation, which is essentially the same as the one I showed you earlier for this probability Q of C and C prime, except you have one more matrix A here. So here I'm looking at the M. The process. The current entering the system at the left side. It works more or less the same. You just have to move your matrix A. But so for the current entering the system, so you have this additional matrix that verifies this algebra. You have also an algebra with D, but it's not really needed. And you can, play the same thing that I showed you here. You can write everything in terms of the A difference, and then you can show, yes, important point. Here I'm talking about open boundaries with alpha equal beta equal 1 alpha. I will tell you what the difference in the general case. But so in this case, this transfer operator are just a very simple expression from which you can, again, easily take the scaling limit. It will give you Wiener processes. And so then, you have some representation of, right, maybe I didn't explain it. So in order to get your eigenvector up to some order En in log G, you need to iterate this matrix, this transfer operator U of G n times at least. And so if you're interested in things up to order n in log G, so you apply it 10 times and you get something like this for this, this correction to stationary large deviation. So this is for this special case here. For periodic boundaries, it works also the same essentially, except you have a trace instead of having boundary vectors. For general alpha beta, you don't have one transfer operator, but you need to use two transfer operators, both of which have the same, the same kind of matrix product representation, except with different boundary algebra. And so you need to iterate, let's call them U and T, and you need U times T. You need to iterate U times T n times to get your stationary eigenvector. Okay, so and now once you have these random walks weighted by, these average of random walks, well, it's quite easy to in the scaling limit, while you get some Wiener processes. for your correction to stationary large deviations. So, I mean, you get some expression like this, some average like this, or you can actually rewrite this in terms, so here the WJs are independent Wiener processes, but you can also rewrite this in terms of non-intersecting Wiener processes. You can show that this expectation value, it can be written in terms of as a conditional probability of non-intersecting Wiener processes. And here, so for S positive, and this parameter S now enters as a shift in these Wiener processes. You get some exponential random variable with parameter S. So, I mean, this is another expression for this. And so, for instance, from this, you can compute the cumulants of the 8 at late times. So, for instance, for the average 8 here, so, I mean, the stationary, the corresponding stationary cumulant is equal to 0. But what you get from this is that the average contribution of the current of the 8 depending on the initial condition. So the initial condition is specified by some function h0 of x, h0 of x, the initial 8. It's just the average of the minimum of h0 minus Wiener process, average over the Wiener process and h0 if h0 is random. And so on. So you have also expression for the higher cumulants. So this, I mean, works for any initial condition. So that was the first part. So now the next part is how to do the same thing, but with better ansatz instead of this iterated matrix product representation. So better ansatz for TASEP, so most of you probably know about it. So, I mean, we try, at least for periodic boundaries, we try some linear combination of plane waves for the eigenvectors of the Markov operator or the deformed Markov operators. And so for periodic boundaries, I mean, the wave numbers of your plane waves are quantized by these Bethe equations. And so there's a peculiarity in the case of TASEP. You see that the Bethe equations, I mean, the Bethe roots Zj are not all that coupled. If you introduce this product of the Zj, then they essentially decouple because, I mean, you just now have some function of Zj and B equal to 0. So in terms of this parameter B, I mean, things are simple. But so if you consider only the non-deformed Markov operator, this is a bit of a problem because, I mean, B is not arbitrary. But now if you consider the deformed Markov operator, M of G, then you can see B as another parametrization as instead of G. So instead of having your matrix parameterized by G, you now have your eigenset, which are parameterized by B, which is just as good. And so from this, it's actually quite easy to compute the eigenvalues. And now, I mean, you have some parametric expression of the eigenvalue as a function of B and this parameter G as a function of B, which give you this kind of parametric expression I've shown you a bit earlier. I'm going to show you again in the next slide. So this is for periodic boundaries. Now, for open boundaries, things are more complicated. So initially, there was some first attempt by De Geer and Hessler. So they found some Bethe equations. Unfortunately, these Bethe equations don't have this kind of simple, I mean, you can't decouple the Bethe roots in them. So it makes things much more complicated. But it turns out, and this was shown by these people, it's really just a conjecture from numerics. So, I mean, what they did, they were just looking at the stationary eigenstate, but I mean, I checked, this actually works for any eigenstate. There are some Bethe equations which have exactly the same form as the ones for periodic boundaries, where with some parameter B here, which decouples all the Bethe roots. So, I mean, it's quite remarkable because, I mean, if you think about periodic boundaries, I mean, you just have one set of Bethe equations. You have several ways to prove it. You can do coordinate Bethe ansatz, algebraic Bethe ansatz, but you always end up with the same Bethe equation. For open boundaries, it seems that there are different procedures from which we end up with different Bethe equations, and some of them, I mean, these ones, are much simpler. So there seems to be a better way to do things. Unfortunately, in this case, we don't know how to derive this. The eigenvectors are missing, so we don't know the procedure yet to get this. But I mean, this is probably something something quite interesting to do. I mean, for open boundaries. And so you can also look at systems with several types of particles. So it's again integrable. Now, if you have two types of particles, let's say you have two currents. And so you end up with two parameters, G1 and G2, corresponding to, G1 to the power H1, G1 to the power Q1, G2 to the power Q2. And in the Bethe equation, it corresponds to two parameters, B and C. But you have the same kind of expression, and so things work essentially the same. And so for stationary large deviations, so for the eigenvalue corresponding to with the eigenvalue with the largest real part, this parametric representation gives you a parametric representation for the eigenvalue, which is essentially always the same. So the eigenvalue is some function of this parameter u, which is a scaling limit of the parameter b, which appears in the Bethe equation, and the parameter s, which is coupled to the current or the height, is the derivative of this function chi. So this is not obvious at all why it will be a derivative. Principle, you could expect to get two distinct functions, but this is another puzzling thing, is that you get some, this kind of structure. And so the function chi you get depends on your boundaries. So for periodic boundaries, you get a polylogarithm. For open boundaries, you can do it for any alpha and beta. So here are two simple cases. For second class particles, so at least alpha equal beta equal 1, it's done. And so, this function, if you specialize it to some variable equal to 0, you recover one of them for open TAZEP, which is a bit strange. I don't have any explanation for this. Another thing, so this is for the KPZ fixed points with boundaries in the long time limit. Now, if you look at the KPZ equation on the infinite line, you can look also at large deviation at short time, that is large deviation around the equilibrium fixed point. And it turns out that the same function also appears, which is, we don't have an explanation for this. For the, let's say, sharp wedge initial condition on the infinite line, you get this one. For on the half line, for some kind of initial condition, I don't remember, you get that one. And this is, again, completely unexpected. It looks a bit like if you had some system with conformal invariance on a torus, the two limits looks like a very long torus or a very large torus, so it will be something like a kind of modular invariance But I mean, for KPZ, you don't really expect that kind of thing. So, I mean, we don't have an explanation for this. So this was for the eigenvalue, but now what I'm interested here is this, I mean, the contribution of the stationary eigenvector. So this kind of combination here, which give you the correction to stationary large deviations. And so it was observed around 10 years ago that for simple initial condition, in case of TAZEP with periodic boundaries, you have rather simple expression for, this combination here, in terms of kappa, where kappa is the logarithmic derivative of the variable g. So the variable g is the variable which is coupled to the current, and the variable b, which is the variable coming from Bethe ansatz. It's essentially something quadratic in kappa, and so you can show this from the non-formulas of the eigenvectors from Bethe ansatz. Now, as I told you, for open TAZEP, we don't have the eigenvectors, so in principle, we can't do anything, except that, since you have these rather peculiar expressions, you can try to see if there could be some similar quadratic expression also for open boundaries. And it turned out that there are, so you can check that with high precision numerics for the eigenvectors after direct diagonalization. So, even with open boundaries, you can define this function kappa. So it has a very different expression in terms of the Bethe roots, but it can be defined. And it turned out that in some cases, for some simple initial condition, so essentially stationary initial condition for these simple values of alpha and beta, and also the initial condition where your system is either completely empty or completely filled for alpha equal beta equal 1. You have also simple expressions for these, this combination here, from which you can guess, you can get this correction to stationary large deviations. And so you end up with, for alpha equal beta equal 1/2 from this, with the formula I showed you earlier when comparing the two approaches. So in this must be equal to this. So this was for the long time limit, so I don't have much time left. So I won't go into the detail of the last part about the finite time dynamics. But the thing is, the important thing is, so you have now a matrix M of G, so a metric which depends on the parameter G. And so, a matrix which depends on a parameter, you know that it defines you a spectral curve, determinant of lambda identity minus the matrix of G. So this is actually an algebraic curve. It's a polynomial of the eigenvalue and the parameter G is equal to 0. And so this complex algebraic curve, after some procedure to remove the singularity, you get a Riemann surface. And it turned out that Bethe ansatz, this, for instance, this equation that you get from Bethe ansatz, give you a rather explicit expression for the way the sheets of the Riemann surface are connected with one another. So for instance, an eigenset is the same thing as choosing some Bethe roots, so choosing some solutions of the Bethe equation. So for instance, choosing some solution, n solution of this among L for the system with periodic boundaries. And in this case, well, I mean, you can from this kind of equation see where your branch points are. It turns out that you have very few branch points, so either 3 branch points for periodic Tazep and up to 5 for open Tazep in terms of this variable B. So you know how to go from an angle set to another one when crossing the branch cuts corresponding to these branch points. And you can reconstruct from this the whole Riemann surface corresponding to your parameter-dependent matrix here. And then, I mean, the functions, the function chi, for instance, I talked to you about earlier. Now it becomes a function which is meromorphic on this Riemann surface. And in particular, you can write the finite time probability of the rate in terms of the contour integral on this Riemann surface. Okay, so I'll stop here. Thank you very much.